शुरू करता हूँ रब के नाम से जो निहायत ही रहीम बड़ा मेहरबान है। The topic of this video lecture is Gauss's divergence theorem। बहुत इम्पोर्टेंट थ्योरम है और इसको समझने की ज़रूरत है, नॉट ओनली मैथमेटिकली बट कॉन्सेप्चुअली एज वेल। तो लेट अस बिगिन विदाउट वेस्टिंग एनी टाइम। लेट्स गो टू say a point charge which is a source of non-uniform electric field. These are electric field lines that I am showing. These are electric field lines due to this point charge. Now suppose I want to calculate flux through a hypothetical surface S. Here, closed surface S. Is this a closed surface S? And I want to calculate flux through it. Electric flux. We know that electric flux phi is equal to integral E dot dS, surface integral of electric field over this surface, or this closed surface. That means what you are doing is you are dividing this surface into infinitesimally small area elements dA. Say here is a particular area element dA. And first you are calculating little flux through this dA, that is simply EdA, electric field strength there, and the dot product of that with dA. Little flux through this. Total flux through the surface is then this integral of these products, these little products. Now you already know this thing, and assuming that you know this thing, let's move ahead. We know if we are asked to calculate flux through this surface, one way that we already know is we will evaluate this integral on the surface. For that, there is what we need is symmetry, other things that you have already studied in your 12th class. But today, my topic is not this. Today what I want is that we will discuss another method of finding flux through this closed surface, electric flux through closed surface. What is that method? The method is look at this volume enclosed by the surface S. This is the volume enclosed by the surface S. Okay. Please be mindful. This we are not discussing a two-dimensional case. It is a three-dimensional case, and in this three dimensions, this is not a line. This closed curve. It is a closed surface, and this is a volume, a three-dimensional thing. This is a two-dimensional thing. Okay. Now I will show you now first how to calculate flux by another method. That is, we will divide this enclosed volume into very, very small elements of volume. Each element will be infinitesimally small, and we can take its shape for convenience because that makes our calculation simple. For convenience, we will take shape of each infinitesimal cube as each infinitesimal volume element as cube, that of cube. So you can think of this that as if this volume, this is S, and this is the volume enclosed by S. Now just have a look at this. This volume is to be divided into very, very large number of infinitesimally small volume elements. This is what I am doing. I am dividing this volume into infinitesimally small volume elements. Okay, let me focus on this cube, this little cube here. Of course, it does not appear to be cube. It better appears to be a rectangle. But we have to keep this thing in mind that it is a three-dimensional case, and hence this is not a rectangle. It's a cube. When I will calculate flux through this cube number say 1, it has a right face, left face. This is left face, and this is right face. It has a right face. Now look at the right face. You will while calculating flux through this cube, through all the cubes and adjust cubes, particularly cubes adjacent to it. Let us take this cube number 2 then. After 1, we will take cube number 2. After 2, we will take cube number 3. So when we calculate flux through this phase, right phase of cube number 1, it will come out to be, it is, look here, it is electric field, suppose electric field directed that way, and for simplicity you can imagine this electric field to be purely horizontal, not like this, a pure horizontal field, perhaps made by set up by a capacitor. Now you have an electric field line here entering into the cube number 1 here. At this place it is entering into the cube number 1, and when you calculate flux through this surface, this flux through this phase will come out to be negative. Why? Because electric field line is directed this way, and normal to the cube, outward normal to the cube is directed like this outward normal to the cube. The angle between the two, electric field and outward normal, is greater than this 90 degree. It is obtuse, in fact it is equal to 180 degree. Now cos, EDA, E dot dA is EDA cos theta. So it will be EDA cos 180 degree. That will be minus, flux will be negative. Okay. So when this phase is counted with this cube, flux through it is negative. But when the same phase is counted with this cube number 2, flux through it is positive, because with phase number 2 and cube number 2, now this is cube number 2, electric field is leaving like this. This is the normal, outward normal now. Normal and electric field line have angle 0 degree, and flux through this is then positive. So what does it mean? It means that when this phase, let's give some name to this phase, say 1 and 1, 2, we have already actually used it. Let us say A, phase A, call this A. When A is counted with cube 1, it contributes negative flux. When it is contributed with cube 2, when it is counted with cube 2, it contributes positive flux, equal positive, equal negative. And when the total flux these two is calculated, this flux through this cancels out. It's a very interesting result, a very, very interesting result. This means that if you calculate flux through this bigger cube, which is formed from these two cubes, as I've shown, this partition, the middle partition, does not matter. It is as if it is not there. So it is as if we have this situation with no partition there. Similarly, when flux through this is calculated, this also forms a part of two cubes. Part of cube number 3, for cube number 3, flux through this is negative. For cube number 1, it is positive. It cancels out. When finally we add up fluxes through these 3 cubes, this also cancels out. Similarly, this will cancel out. Similarly, this will cancel out. Similarly, this will cancel. Until you reach the surface, this will remain. There will be nothing, no other cube that can cancel flux through this. We will be left with flux through this. So this means that this array, all these. Now similarly, now look from this side. This phase is common to these two, so it will get cancelled. This phase is common to these two, it will get cancelled. This space is common to these two, it will get cancelled. This space is common to these two, it will get cancelled. What will be left behind will be this. So we are left with two pieces. Say one here, one here, one here. Similarly, when you add up these fluxes from these, now consider this, cube number 4. These two have a common phase, that is this. When counted with 4, it will give you positive flux. Negative. When counted with 1, it will give you. When counted with it's not even 2, it is say 5. When counted with 5, it will give you negative flux. So this will cancel out. Similarly, this will cancel out. Similarly, this will cancel. Similarly, this will cancel out, leaving us with this. Similarly, this will cancel out, leaving us with this. Now you can better easily, I think it is now quite easy for you to understand. If we find out flux, electric flux through all the cubes inside this volume, into which the volume is divided, and add that flux up, we will get flux, net flux through the outermost surface. This is important. This is very, very important. It is as if someone is telling you that there is a room like this, and inside the room, there are a number of, say, these water, these faucets, which actually are pouring water into the room. These are pouring water into the room. And this water is filling up the room, and then is leaking through, say, it is windows, it is window here, it is window here, say door, through this. To calculate how much water is leaking through this, you have two choices. Either to sit at the doors and windows and collect that water in buckets. That is one choice. That is this. That is this. Another is do one thing. That is go inside this room and see how much water is being poured by each faucet into the room. Add that up. That will give you total water that is leaking through this. A rough example, of course, a rough example, but it may help you in understanding what I am saying. So, dear students, with this thing that you understand what I mean flux through this surface can be calculated by dividing the volume inside the surface into very, very small volume elements, cubes, and then adding up the flux, calculating flux through each cube, adding up the fluxes through all the cubes. And in that process, what will happen? The inner surfaces, all flux through all the inner surface will cancel out, leaving us only flux through the outermost surface. And suppose we do it now. Let us begin. Let us take one of the cubes from among them. Okay. One of the cubes. Say, suppose here is the cube. Here is the cube. This is the cube that I am going to use. The cubes are not so large as I am showing here. I am showing it here only for clear understanding, or your clear understanding. Okay. Now you have it here. This is the cube. We make certain simplifications. Initially, let us begin with a field that is purely horizontal, that is, which is directed. If we take x-axis along the horizontal, y-axis along this, and z-axis along this, then the field that I am speaking about will be directed along x-axis. It won't be having any y or z component. We will add up those components later on. Let us first begin with the simple case. So you have an electric field like this. So suppose there is an electric field line. I would show many lines in order to avoid any jumbling. Now I'm going to show you just one line. Say there is this line, electric field line. Now this electric field line passing through this surface. And one more thing, that is, let's choose if origin is at the, suppose if origin is here and the cube that I'm speaking about has the nearest nearest corner to the origin, this, then let us choose that as the origin. Suppose this is the nearest this corner to the origin. This will be our not sorry, I what I said. Let us, when we choose origin here, there is no question of choosing origin there. I mean, if origin is here, then let the coordinates of the point nearest to the origin be say x, y, z. Now let this be delta x, this x-axis, and this delta x. Let this be delta y. Let this be delta z. Z-axis is in this direction. In this direction. Y-axis in this direction. Okay. Now, two interesting things emerge here. That is, if then this is very important. If the field is uniform, that means if Ex, since we are considering only x component of the field, if Ex is not a function of x, does not change with x, that means it is constant along x-axis. That means it is field of this type, constant along x-axis. Then net flux through this cube will be 0. Why? You can see yourself. First of all, this phase, so far as this phase is concerned, electric field line runs parallel to it, hence it does not contribute to flux. Electric field line runs parallel to this phase, it does not contribute to the flux. Electric field line runs parallel to this front phase, it does not contribute. To the back phase, it does not contribute. Only it pierces through only this phase. Let me call this phase number 1 and let me call this phase number 2. This 1 and 2. Now, if the field is uniform, like this, just a minute. Sorry. You have electric field like this. Yes. Okay. If you have a uniform electric field, then flux through this will be 0. Why will flux be 0? You can yourself check it easily. When electric field line enters into this, say here, into the surface, it will contribute negative flux because normal, once again, outward normal is directed this way. And if when it leaves here, it will contribute positive flux, equal to this, but positive, not negative. Positive flux, because normal is now this 0, angle is 0 degree. So when we add up these two, what will happen? Total flux will be 0, because flux at this point and flux at this point is equal in magnitude, but has opposite signs. Why it is equal in magnitude? Because electric field here and electric field here is same, uniform. It's uniform. That is why. If we call electric field at this phase as Ex1, and electric field at this phase Ex2, then Ex1 is equal to Ex2, makes this flux 0. However, if the field is like this, if there is a variation. Now, electric field at this point, Ex1c, will be more. Electric field at this point will be less. Then, when we add up these two fluxes, flux here and flux here, they won't cancel out. We will get a net flux. Okay, that is very important. And see, where do you get net flux? If you look at this, you get net flux where electric field lines diverge. You see, there is a divergence among these lines. The distance between the lines changes. They go away from each other, or they could, of course, approach each other. They are not parallel like this. The distance between the lines is not same here. Now, with this thing, a very important thing that we find is that flux is zero, then divergence is zero. Flux is non-zero, divergence is non-zero. Net flux through this is zero, and there is no divergence. No divergence among these electric field lines. Now, to calculate net flux through this, that is quite easy now. Calculating net flux, and in this case, we will now suppose that Ex1 and Ex2 are not equal. They are not equal. So we have this situation. Net flux through phase number 1, phi 1, delta phi 1 is equal to flux through phase number 1, that is equal to delta phi 1. You can yourself see Ex1 into area. Electric field into area. What is the area of this? Area of this is, this is delta z, this is delta y. So the area of this phase is delta x, delta y, delta z. This is minus. Why minus? Because angle is obtuse here. Now, flux through phase number 2 will be equal to minus Ex2 delta y, delta z again, because area of that is also delta y, delta z. Okay, then therefore net flux through these two phases, 1, 2, will be this positive there. So it will be Ex2 delta y, delta z minus Ex1 delta y, delta z. That is equal to Ex2. Now Ex2 minus Ex1 delta y, delta z. Now, the variation of electric field along x-axis, that means it varies. Suppose Ex2 is more than Ex1. Suppose it could be less, it could be more. That depends upon its rate of. Now, how much is this difference between the two? We can approximate this difference by a simple form of Taylor's theorem. Simplest form of that is without invoking Taylor's theorem. Let us simply go and say Ex2. Suppose it is not this type of field. Suppose it is this type of field. That means the electric field is increasing with distance. Okay, Ex2 is equal to now. It is not must. You could take this case as well, but this case makes things easier for you to understand. So Ex2 will be equal to, suppose it is Ex2 here, and it is Ex1 here. electric field increases from this point to this point. So what will be the value here? This is final value, this is initial value. So final value is equal to initial value plus change in value. Of course, plus change in value of Ex. Okay. But how much is the change in value of Ex? That depends upon how fast it changes from this point to this point. That depends upon its rate of change. So we can write this Ex1 plus this is delta Ex, that is dEx, del Ex by del X. This is rate of change of electric field with respect to X. Rate of change means how much does electric field change per unit change in X. If you now want to calculate total change in electric field, then multiply it by change in X from this point to this point. It is simply unitary method. That means if you know rate of say books, say physics books of 12th class is 100 rupee rate. What is when we say rate of physics book is 100 rupee? It means that cost for one book is 100 rupee. This is this rate of change of electric field with respect to this. That means how much does electric field change with a unit change in X, with 1 unit change in X. Now, but we did not change X by 1 unit. X changed by delta X. So how much? Suppose we did not purchase 1 book. We purchased 10 books. How to calculate that cost? Multiply that by 10. Multiply this by delta X. So my dear students, I think this is clear to you. Now, you can write X2 minus, take this on this side Ex1 is equal to when I transpose this to this side, I am left with del Ex by del X, delta X. Okay. And when I substitute this in this equation, in this flux through this resultant flux through these two phases 1 and 2, I have Ex2 minus Ex1 delta. This replace this by this, but keep these things there. So you will have delta phi 1 2 will be equal to delta phi 1 2 will be equal to Ex1. Sorry, it will be equal to not that Ex1. It will be del Ex by del X this much into del Y del Z. Similarly, we can now consider Y component, and for Y component we will get, if we write that in this phase number, if we write it phase number 3 and 4, say this is phase number 3, this is phase number 4, then there phase number 5 and 6 front and back. So we will have delta phi, this net flux through those two phases will be 1 2, that will be 3 4, will be del E Y, del Y, del X, del Y, del Z. Sorry, delta X, delta Z. Similarly, net flux through phase number 4, 5 and 6 will be del EY, EZ, del Z into del X, del Y, del Z. Total flux through the surface then will be through this little cube will be total flux through this little cube. When we add up all these fluxes will be E dot dA through this cube. E dot dA it will be equal to that will be equal to sum of these delta Ex, del Ex by del X by del X. Okay, you know this is common to them, so plus del EY by del Z, del E sorry, del Ey by del y, del Ez by del z into delta x, delta y, delta z. That is simply volume of the cube, del V. Okay. Now, if you want now the total flux through the surface S, total flux through the surface S, that will be integral of these. See, you will have to take integral of this. That will be integral total flux. Sorry, it will be E dot dA. That will be integral of this. Integral of this S del Ex by del x plus del Ey by del y plus del Ez by del z, sorry, then dV. Now, but what is this? This is divergence. How? Because we know if Ex varies with x, only then there is divergence. If Ey varies with y, only then there is divergence. If Ez varies with z, only then there is divergence. If any of these quantities is zero, the whole thing will be switched off. I'm sorry, not that any. If all these three quantities are switched off, that are zero, then there will be no divergence at all. So this is a very important relation between flux, electric flux, and divergence. Look at this relation. There is one thing that I must correct here. That is, you have to write it as volume because you are now taking this volume as your variable and you are integrating here or volume. This is a volume integral. This is a surface integral. And you know, if you can easily recognize it, this is simply you have E is equal to I Ex plus J Ey plus K Ez. This is E and this is say now you know the del operator I del by del x plus J del by del y plus K del by del z. Now you know dot product, the strange product, that is which is del dot E. Del dot E is equal to dot product is this del by del x Ex plus this del by del del y Ey plus del by del z Ez. So this is what we call divergence. For divergence to be there, this must be there, this must be there, this must be there. At least one of the three must be there. So that is the story. And then see, this is what we call Gauss's theorem. This is Gauss's theorem. And in physics, what do? We think of Gauss's theorem as a theorem that connects surface integral with volume integral. We often switch from one integral to another integral, as we will be actually discussing immediately in our next topic when we take up conservation laws in electromagnetism. So we will be using this theorem, a very useful theorem. We will, if God wills, we will be also discussing Green's theorem, Stokes' theorem in future. I will be before ending this lecture, I can replace this by this quantity, and I will have integral E dot dA, E dot dA, integral E dot dA S is equal to V volume integral of, now you know this quantity is del dot E, so it is del dot E dV. Now this is the Gauss theorem. Important thing is that Gauss theorem tells us that there are two ways of calculating flux through a closed surface. One is sit on the surface and make all calculations there. Another is don't use surface, use the inner volume and make calculations there. Now these two ways of alternative ways of looking at things, these have come to be to occupy center stage in physics in a form that is called AD-CFT. Just remember at this stage, just remember one thing, that is Gauss's theorem tells us that the same thing, that is electric flux. Our example is electric flux. I will not like to burden you with those examples which I am not going to discuss. Now, when you calculate electric flux, there are two ways, and two ways are equivalent. They are equal. On one side you have this calculation of integral on the surface S, on the other side you have calculation of flux integral throughout the volume. Thank you for being with me. Please don't hesitate. If you have some confusion, please convey to me through say comments. Thank you so much.